Now we will learn about type 2 self-catalyzed polymerization. Okay, if you still remember from our previous lecture, okay, stack group polymerization can be divided into two types, which is the first type is type 1, which is catalyzed polymerization, or also known of polycondensation reaction. So from type 1 polymerization, we have learned about the degree of polymerization and how to do derivation for the kinetics of polymerization. So today we move to the second types of stack growth polymerization, which is known as self-catalyzed polymerization, which is a reaction that didn't use the addition of catalyst. So the polymerization is also known as self-condensation reaction. So in this polymerization, we can see the example of the polyesterification reaction without acidic catalyst. So in self-catalyzed polymerization, this type of reactions is carried out in the absence of externally added strong acid. So in this reaction, we didn't add any catalyst, so there is no acid catalyst. Therefore, in the polymerization of polyester, so the diacid monomer act as its own catalyst for the esterification reaction. So for this case, the HA, we know that this is the symbol for acid. So because this reaction don't use any acid, so the acid is replaced by the functional group of diacid, which is COOH. So the equation can be written as uh, decomposition of functional group of carboxylic acid dCOOH over dt can be write as KCOOH squared and OH. So I will show you on how we obtain this expression in the next slide. Okay, to make easier for you to understand, let refresh back from what we have learned previously. So you know that rate of polymerization, okay, can be written as constant times concentration. This is concentration of the all the monomers involved, the concentration of the reactant. So rate of polymerization is similar to the decomposition of a monomer in a reaction. So it is written as the decomposition of a monomer A over dt. So this is the general expression of on how you find the rate of polymerization. So it is constant times concentration. So next I will show you the rate of polymerization of catalyzed system and uncatalyzed system. From what we have learned, there are two types of stack growth polymerization reactions. So the first one is catalyzed, and then the other one is self-catalyzed. So this is type 2. This is type 2 reaction. Okay. Type 1 Catalyzed reaction is what we have learned previously during our face-to-face class. So if you still remember, the rate of polymerization for catalyzed reaction can be written as decomposition of carboxylic concentration over dt, and then equal to the constant K3K times concentration of all reactant, which is COOH, OH and HA. Okay, we have HA because in catalyzed reaction, okay, we use acid to assist the reaction. But in our self-catalyzed reaction, okay, self-catalyzed is the reaction that did not use any acidic catalyst. So the HA, the acid here, is substitute with the concentration of the monomer. So for uncatalyzed, the rate of polymerization can be rewritten as, so this is the rate of polymerization. So we substitute the acid with carboxylic acid concentration. So it's K3K times COOH times OH, and then we substitute acid because it don't use acid with concentration of carboxylic acid COOH. So in this constant K3K can be combined with capital K here. So you combine the constant into one constant, and then you simplify this. So we got COOH squared times OH. So this is the rate of polymerization for type 2, self-catalyzed polymerization. Okay, so rate of polymerization, okay, from what we have discussed previously, we can combine the constant K and K3 into experimentally determined rate constant K. And then, so from that equation, we can say that in self-catalyzed polymerization, so this kind of polymerization is fully dependent on the carboxyl concentration, COOH. So for most polymerization, the concentration of the two functional groups are very nearly stoichiometric, where we can say that the rate of polymerization, okay, in a general expression for uncatalyzed type can be written as negative dA over dt equal to constant times A cube. So this is the general expression for the rate of polymerization. For better understanding, let's compare the general expression for rate of polymerization between catalyzed reaction and uncatalyzed reaction. So from what we have learned before, so the rate of polymerization for catalyzed reaction can be written as decompositions of concentration monomer A over dt equal to the constant times monomer A and monomer B. But according to the characters equation, so it is stated that the concentration of monomer A is equally the same with the concentration of monomer B. So this expression can be rewritten as decomposition of monomer A over dt equal to Ka, because B equal to concentration A, so Kaa, and then we can simplify this equation. So rate of polymerization is equal to the constant times concentration of monomer A squared. So this is for the catalyzed. This time is uncatalyzed, which is also known as self-catalyzed. So the general expression for self-catalyzed reaction is dA, concentration A over dt equal to Ka squared times B. So again, okay, according to the characters equation, K concentration A equal to concentration B. Therefore, this equation can be rewritten as dA over dt equal to Ka squared. We change concentration B into A. So the final equation will be constant Ka cube. So this is the difference between the catalyzed system and self-catalyzed system. Okay, from the general expression of rate of polymerization for self-catalyzed reaction, we can use that expression to write the new expression for degree of polymerization. So, what you need to do is you integrate the expression for the rate of polymerization before, okay, from which is negative dA over dt equal to Ka so you integrate this equation and then you get this equation 1 over A squared minus 1 over A naught squared equal to 2 kT. So you integrate this equation and you got this new expression. So when you want to relate with degree of polymerization, we know that degree of polymerization is equal to the concentration A naught over concentration A, which is equal to 1 over 1 minus P. So this is a general equation for degree of polymerization. So from this equation, you can get the value of concentration A, which is you got concentration of A naught times 1 minus P. So this is the value of concentration A. So you can put the value of concentration A into this equation. So you will get when you substitute the value of concentration A, so the final equation that you obtain is degree of polymerization equal to 2 kT times concentration of initial A squared plus 1. So this is the expression of degree of polymerization for uncatalyzed reaction. These graphs show the difference between degree of polymerization of catalyzed system and uncatalyzed system. So this is the expression for catalyzed system, which is degree of polymerization equal to the concentration A naught Kt plus 1. Meanwhile, for uncatalyzed reaction, so degree of polymerization is equal to the degree of polymerization squared equal to 2 kT times A naught squared plus 1. So if you want to compare between these two, you can see that the molecular weight for catalyzed reaction increase sharply throughout the reaction because you have assistance from the catalyst, which is acid. But for uncatalyzed reaction, because it is self-catalyzed reaction without any assistance of catalyst, without any assistance of acid, we can see that the molecular weight increase more gradually than when acid catalyst is added. So the acid is the molecular weight increase slowly and gradually throughout the reaction.